Alright, this is the third and final part of our test on radical functions. In this video we will focus on transformations of radical functions and how those transformations appear in the functions. So looking at number 12, we're supposed to use the description to write the square root function that is reflected across the x-axis, translated 10 units up and 9 units to the right. So let's see. Alright, so a square root function that's reflected across the x-axis. Now that shows up as a negative sign in the front when it's reflected across the x-axis. So then we'll have the square root. Alright, now the 9 units to the right, that happens on the inside of the function. Now it should be the opposite of the way it looks, so to the right will actually be minus 9. So this would be 9 units to the right. Now 10 units up, we'll have to put a plus 10 on the outside of the radical, and that would be 10 units up. So that is number 12. Let me make this a little bigger. Alright, so number 13. Again, we're supposed to create a square root function, but this time we're given the domain and the range. Okay, so the domain being 4 to infinity. The parent function for a square root function starts out like this with it starts out at 0, 0. So this would be the parent function. So if it's going to have a domain of 4 to infinity, that means it would have to be shifted over to the right by 4. Okay, so it'd have to be over to the right 4 so that the domain could become 4 to infinity. So the key is looking at this and understanding that this represents a shift to the right by 4. Okay, so when we begin to write that equation, okay, so that's f of x equals, alright, so if it's to the right by 4, then that's going to mean x minus 4. Okay, just like on problem number 12, 9 units to the right, we had to do x minus 9. 4 units to the right would be x minus 4 on the inside. Now, how about that range? What's going on with the range? So for the range to be negative infinity to 2, alright, so 2 things have to happen. So, this was not the actual graph. I was just focusing on the 4 to infinity part. This won't be the actual graph either, but I'm just going to focus on the range here. If the range is negative infinity to 2, the only way that could happen, first of all, 2 now has to be the highest value on this graph. Okay, so it has to be up here at 2, so negative infinity to 2. So it has to be coming up from the bottom and then to 2. Okay, so it has to be doing this type of a thing. Okay, if it would go from negative infinity to 2, negative infinity to 2. So that means 2 things. You see how compared to the parent function, which curves upward, this is curving downward. So that means there's been a reflection over the x-axis that happened. Okay, so let's talk about that. It's upside down, so that means we're going to need a negative in front to capture that. But then also it's been shifted up 2. So we're going to need that plus 2 on the end to capture that. Alright, of course, if I put both of these things together into one graph, okay, to where it's shifted over to the right 4, and it's up 2, and it's upside down, okay, that would actually look more like this. Alright, it's got to be to the right 4. If I put that all into one nice graph, that would look like this. Alright, so it's to the right 4, but it's also up 2. So that would be like here, and it's upside down. Okay, so this is what it would actually look like. But here's the equation. Now, number 14, very similar. We need to create a radical equation that will, okay, it's actually not similar at all. Except for, once again, we're creating an equation that fits this description. We need one that will not have a solution, and we want to explain why it won't have a solution. Well, some of the problems that we've seen that had no solution involved, if you had the square root of a number or an expression, say if we had the square root of x, well, we're making an equation, so not just a function, so forget about the f of x part. If we had the square root of some expression, and then that was going to be equal to a negative number, we learned that there's no way that could happen. There's nothing you can take the square root of that's going to give you a negative answer. So that's would be an easy way to come up with an equation that had no solution. And this would be a really simple one right here. So boom, that's an answer right there. So this is one whole category of ways to do it. And so you could put anything in here that you want. You know, I could put x plus 2 is equal to negative 4. Or, you know, so if you had the square root of anything and then equal a negative number, boom, that's definitely going to have no solution right away. And that's the easiest, that's probably the easiest way to create something that has no solution. Okay, so explanation, I'm going to say something like, there's nothing that you can take the square root of that will give you a negative answer. Okay, now that's really the end of the radical function portion of the test. The rest of these problems are review problems from previous units. So if you're just interested in practicing and studying radical functions, you can stop the video now, because the rest of these will be sort of irrelevant to that. Alright, but we make a habit of throwing in a few review problems just to make us reach back into our memory bank and pull back some old information. And that's actually a good way to learn. Every time you reach back for old knowledge, it really reinforces and helps you to remember it for the long term. Anyway, so number 15, if we want to solve this inequality and write the answer in interval notation, you're going to want to factor it. Okay, so let's see if we can factor this. So let's see, 3x squared is 3x times x, 12. Now, as I'm looking at 12, I'm thinking of many possibilities. It's either 3 times 4, or it's 2 times 6, or it could even be 1 times 12. Let's see, let's try the 3 times 4 option. If I'm going to go with that, I know I cannot put the 3 here. Alright, this is no good because that would cause a GCF, right, a common factor. And if there's no common factor in the original trinomial, there won't be any common factors in the binomial either. So I would skip that order, and I would only try the 4 times 3 option. Now inner plus outer has to equal middle. So inner, I've got 4x. Outer, I've got 9x. Can I get a negative 5 out of that? Sure. If I have a positive 4 and a negative 9, that will make negative 5x. So there's my positive 4, and making this 3 negative will give me the negative 9 that I'm looking for. Also, that'll give me negative 12 because a positive times a negative is negative. So this is the correct factorization. Now, we actually need the zeros of the function to start off and make a nice number line graph. So we will actually take these and set them equal to 0 because we want the zeros of the function. Okay, and x minus 3 equals 0. So, subtracting 4 from both sides, adding 3 to both sides. So this gives me 3x equals negative 4, and this gives me x equals 3. So that's one of my zeros. Meanwhile, over here, dividing by 3 on both sides, I have x equals negative 4/3. Okay, so this is my other 0. And negative 4/3 is, just as a decimal, is approximately equal to negative. Now, so even on a 4-function calculator, I could do 4 divided by 3. And that's negative 1.3 if I round it. So negative 1.3. So that's going to be good to know. So let's make a number line graph, starting off showing where the zeros are. Okay, so if I do that, okay, so I have this, negative 1.3, or in other words, negative 4/3. And over here somewhere, I have 3. Okay, so these are the zeros. These are where the function equals 0. So, will these points, will the zeros be indicated by open circles or closed circles? That's my next question. Well, this, we want to know where the function is less than 0. Not equal to 0, just less than 0. So we can't include these points because these points are where it's going to equal 0. So that's not what we want. So we will use open circles in that case. Open circles, okay? Now, it's time to do test values. So what we do is we'll make a little chart out of it to help us out. Okay, I'm going to give myself plenty of space though. Okay, we need a test value in each one of these zones. So to the left here, here's negative 1.3. So let's say we'll try x equals negative 2 and see what happens. In between here, 0 is always good, so let's try x equals 0. Over here to the right, how about x equals 4? So this will give us a test value in each zone. Now, look at the original inequality, all right? It is 3x plus 4 times x minus 3 is less than 0. So I'm going to repeat that 3 times. So 3x plus 4 to x minus 3 is less than 0. 3x plus 4, x minus 3 is less than 0. So I'm just going to plug in these x values and see if it makes a true statement or not. So if I put in negative 2, for example, then that gives me 3 times negative 2 plus 4. And then negative 2 minus 3. 3 times negative 2 is negative 6. Okay, so that's negative 6 plus 4 times negative 2 minus 3. Alright, negative 6 plus 4 is negative 2. Negative 2 minus 3 is negative 5. Okay, multiply these together and you get a positive 10. Alright, is 10 less than 0? No, that is a positive number. It can't be less than 0. Alright, what about this? So if I put in 0, then, I have 3 times 0 plus 4, and 0 minus 3. 3 times 0 is 0. So that's just going to give me 4 times negative 3, and that's negative 12. Okay, is that true? Yes. Alright, so we had a no, and then we had a yes. Yeah, all negative numbers are less than 0. And finally, we will check x equals 4. So that would be 3 times 4 plus 4, and then 4 minus 3 plus 4, less than 0. So that would be 12 plus 4. Okay, so that would be 16 times 1. So that would mean 16 is less than 0. Is this true? Clearly no. Alright, so as far as which of these values were actually solutions, negative 2 was not a solution, 0 is a solution, and 4 is not a solution. Okay, so since 0 is a solution, that means all of the values in this zone will be solutions. So we will indicate that by drawing this segment in. We will leave the other zones empty to show that there are no solutions in those zones. So this would be a nice graph of our solution set. But we need to go ahead and have interval notation. So if we do that, interval notation will be, and I'll use the fraction form. So negative 4 over 3 to 3. Okay, so it's going to look just like an ordered pair, but in this context it means the values between negative 4/3 and 3. We use round parentheses and not square brackets for the same reason that we put open circles right here. The endpoints themselves cannot be included because they equal 0 there. But we want only the values that are less than 0, not equal to 0. So that is the final answer. Okay, so including our little graph here, which is good. Okay, but the interval notation is specifically being asked for, so make sure you have that. Alright, and finally for number 16 we will look at intervals of increasing and intervals of decreasing. Alright, so we will read this graph from left to right, and we are supposed to assume that on the ends here it goes forever. Okay, so let's assume that. So as we look at intervals of increasing, alright, as we do this we have to read the graph from left to right. So if you imagine traveling this like hiking, for part of your trip you're going to be going uphill and then downhill and then uphill and then downhill. So from left to right, the uphill part of the journey is increasing. So so starting from right here, and then we're increasing. All right, right up until here. All right, and then we are decreasing. Okay, so we're decreasing, going downhill, downhill, downhill. Okay, and then we begin increasing again. And then once again we are decreasing. Okay, so increasing and decreasing, what are they sort of asking us for first? So first let's talk about the intervals of increasing. So those are the two green portions. Now we're only looking at x values right now. Okay, let me go back to normal. Alright, we are only looking at x values when we are talking about increasing and decreasing. So looking at this end right here, this is, remember we're talking x values. So this is negative infinity. This has an x value of negative infinity. Not because it's going down, but because it's going to the left forever. This end is at an x value of negative 3, right? Some kids had a hard time reading the graph. But, this is 0, so this is negative 1, negative 2, negative 3. Okay, and then looking at the pink part, it goes from negative 3 to 0. This is an x value of 0. And then back to the green, this goes from 0 to 3, an x value of 3. And then over here on the right, this is positive infinity. Again, yes, I see that it's going down, but we are talking about x values. And this is going to the right, so that's an x value of positive infinity. Alright, when you say down, you're talking about y values. So this first increasing interval is from negative infinity to negative 3, looking at the x values. Okay, so negative infinity to negative 3. Okay, and we will keep it round, parentheses. The negative 3 itself cannot be included because we want to know where it's increasing. But notice this negative 3 is the end point for both the increasing and it's the beginning of the decreasing part. Can it be both? Of course not. So the truth is it's increasing right up to negative 3. But at negative 3 is flat. Okay? It goes from an upward facing slope, positive slope. Later it's a negative slope. But right at the top, it's a horizontal slope. Okay? It's neither increasing nor decreasing at negative 3. So negative 3 doesn't get included. So we show that by leaving it round. But anyway, we have another interval, so we need that union symbol. So the other increasing interval goes from 0 to 3, as we discussed. Okay, so 0 to 3. Okay, now intervals of decreasing. So we have two of those. So the first one is here from negative 3 to 0. Union. And then the last one is from 3 to infinity. Okay, and that is the end of this lesson. Alright, I hope it was helpful. I will see you on the next video.